be the fourth lecture of module 11. I am going to talk about error estimates, and we are going to talk about least square fit, and then finally, the last topic that I will do in module 11 is that of correlation functions. So, I will try to cover all these very briefly and fairly quickly, and some of these will be familiar to you. So, I will be able to go fairly fast. Okay. So, we will start with the idea of error estimates, and this is something that you have seen many times, but you might not appreciate some of the intricacies of it. So, you might have seen, for example, that let us say there is an exam, and all of you get marks in the exam, and then what you ask for is what is the average score of the whole class. You might ask the standard deviation of the marks. You might ask things like that. Okay. Now also for example, you might see various data reported in books or other places where they write some value, and then they will give some plus minus some number. Okay. So, they will give some, they will say that they will give a range of values instead of giving one precise value. Okay. And what we will see is that these are actually related to each other, and what we will also see is that there is an underlying assumption that things are following a Gaussian distribution. So, we already saw in the case of the central limit theorem that if you have a very large number of variables, then their distribution tends to look like a Gaussian random variable, and so it is this idea that is underneath the use of standard deviation as an error estimate. Okay. So, we will just go quickly and first talk about error estimates. Okay. So, let me start. So, error estimation. So, suppose you have data x1, x2, x3 up to xn, there are n data, and the data is of some variable x. Okay. Then what you say is that you define the average mu x is equal to sum over I equal to 1 to n x I divided by n, and you define the standard deviation sigma of x as square root of sum over I equal to 1 to n x I minus mu x square divided by n minus 1. Okay. So, this is the definition of the average and the standard deviation. Now we should note, really emphasize again, that the n minus 1 is there to ensures that sigma x is an unbiased error estimate. Okay. Now, I am not going to talk about the meaning of the word unbiased, okay, but you can, this is a technical point. Okay. This is a technical point, and you can refer in read in various books, technical point. Okay. So, this if you are interested, you can look up in Macquarie what the meaning of this unbiased estimator is. I will not bother about that, but I will just say that you need an n minus 1 when you are defining the standard deviation. Now, this is so now suppose you are to report a value. So, what you say is that the best, so if you want to report a value, so to report measured value. So, you imagine that you have taken n readings and you got all these values, and you want to report a measured value. So, what you say is that the best estimate of x is equal to mu x. which seems very obvious. So, the best estimate for x that you can get is the average value of x, okay, and that is what you usually report. Okay, but actually it is a technical point that this is an estimator of x. Okay. Now, now if you ask, so for a single reading, best estimate of error is equal to sigma x. Okay. For n readings, okay, best error estimate in mu x. Okay, so the question is how close do you think mu x is to the actual answer? Okay, so the best error estimate. Okay, now what you would expect, so this is called the standard error of mean. Okay, so it is a error in mu x. Okay, so when you report mu x as a reading, what is the best estimate of the error of mu x? So the standard error of mean, okay, this works out to sigma x divided by square root of n. Okay. So what it means is that your reported value is equal to mu x plus minus sigma x divided by square root of n. Okay. So often you will find that people give the error estimate in the reported value, and that is usually the standard error of mean. Okay. So the point is that if you take any one reading, okay, then the error in that one reading is sigma x, but if you report an average, the error in that average is sigma x divided by square root of n. So therefore, if you make more measurements, then you expect that the error in the average should go down. Okay. So this is a very this is how data is reported. Used to report data, also used to show error bars in graphs. Okay, so suppose you have a graph, okay, and so often what you will find is that your graph will have various points, okay, and each of these points is got by an average over a lot of quantities. Okay. So what is done is that you might do a fitting of the graph, okay, but what is also done is that you show errors on these error bars on each of the readings. And usually if the error bars in two readings overlap, then you say that you cannot distinguish these two readings within the error bars. So for example, this point here and this point here, let me show it in a slightly different color, this point here and this point here. Okay. So their error bars overlap. Okay. So you would say that you cannot actually distinguish, because what you are saying is it is this point plus minus so much, this plus minus so much. So there is a good chance that they are the same. Okay. So you really cannot distinguish these two within the error bars. So what you do in such a case is to make more measurements, so the error bars go down. Okay. So this is a very common practice that you will see often, this reporting of error bars. Also what you will see in you'll also see some of this in statistical mechanics, where what you will find is that the error in readings, okay, error in average value, okay, that becomes negligible. So in statistical mechanics, we calculate average and deviations from average. Okay. But what we will find is that for an intensive variable, this deviation. So suppose you have energy. So for example, you might calculate the Gibbs free energy. So, G, okay, this is proportional to n. So, this is extensive variable proportional to n, where is number of particles. Okay. Now, now in statistical mechanics we do something called an ensemble average. Okay. So, when you make an so what is G is written as the ensemble average, I will show in square brackets. So, plus minus the sigma of G. So, the standard deviation of G okay. So, so it turns out that this standard deviation is to square root of n. Okay. So, then this is proportional to square root of n. So, whereas this is proportional to n. So, this is deviation in a single measurement. Okay. So, this is a deviation in a single measurement. So, basically we can write so in the thermodynamic limit n tending to infinity. So, sigma G is less than average value of G. Okay. Sigma G becomes much smaller, since this is only proportional to square root of n, whereas this is proportional to n. So, for example, if n is 10 raised to 23, okay, this will or 10 raised to 22, then sigma G will be of the order of 10 raised to 11, which is much smaller than 10 raised to 23. Okay. So, basically you can write G is approximately equal to average value of G. Okay. This is one of the things that you do in equilibrium statistical mechanics. Okay. Or you can say statistical thermodynamics. Okay. So, so the idea is that these deviations are very small. Okay. So, your G becomes approximately equal to average value of G. Okay. So, now the next topic that I want to do is least square fit of data. Okay. So, this is something that you have seen many times, and you often do it in your lab. Okay. For example, if you have a table of data, so you have let us say the independent variable. So, this is x 1, x 2, x 3 up to x n, and you have a dependent variable that you measure y 1, y 2, y 3 up to y n. Okay. And now we want to fitting function. We have a fitting function y equal to f of x. Okay. So, how to the fitting function might be linear, okay. It might be quadratic, it might be anything, it might be exponential, anything. Okay. So, typically what you think of is that you have x and you have y, okay, and each point. So, you have x 1 y 1. So, x 1 y 1 might be let us say here, x 2 y 2 might be here, x 3 y 3 might be here, x 4 y 4 might be here, and so on. You might have all these points. Okay. So, so now what you want to do is you want to fit some curve to this, and you might fit a function, you might fit a straight line, you might fit some function that has a shape like this, or you might fit a quadratic function, something like a parabola. You might fit any function. Okay. Now the question is how to choose best parameters for fitting data. Okay. So, in other words f of x. So, what are these parameters? So, for example, So, you can take example f of x is equal to a times x plus b, then a and b are parameters. So, we call this a linear fit and a and b are the parameters. Okay. Other example, you can have f of x is equal to let us say you fit it into, you can fit into any function, you can let us say you can fit into so x square plus x. So, you can fit let us say into a x square plus b x plus c. This is a quadratic fit, and here there are 3 parameters a, b, c. Okay. And you can go on, you can also do other functions. You can do, for example, f of x is equal to a, let me show the parameters in colors. So, a, and you have e raised to, you can have lambda x. This is exponential fit. Okay. You can go to, actually you can take any function. Okay. Now, exponential we have represented by 2 parameters. You can also have exponential, you can also have something like this, f of x is equal to let us say, okay, I will not use colors. So, let us say a e to the lambda x plus b x plus c. Okay. So, you have a sum of exponential and a linear. Okay. And you have many more, here you have 4 parameters. Okay. So, the question is, how do you choose the best values of these parameters? So, for example, if you choose one value of a, b, c, you might get something like this, you might take another value of a, b, c, you might get something like this, you might take a third value, you might get something like this. So, what is the best value of these parameters to be chosen? Okay. So, each value of these parameters will give you a different line. Okay. And how to choose the best values of these parameters? Okay. The answer is you use a least square fit procedure. So, I will explain the procedure. So, what you do is you define error as error in any given fit. Okay. So, that means let me take the example f of x has 2 parameters, okay, a and b. Okay. So, what you do is in any fit you fix these 2 parameters, okay, and you define the error. So, the error is, so y I is the value of y, okay, minus f of x I. Okay. So, x I is the actual data point x I. Okay. So, what we have here x 1 and y 1. Okay. So, what you are calculating is y 1 minus f of x 1. Now, if it was a perfect fit, then this difference would be 0. Okay. But what you will find is that in any fit you won't exactly fit with that point. Okay. There might be slight deviation. So, you define the error as this and sum over I. This I will call it delta. Delta equal to so this is a total error, okay, the square error of any fit. And notice that since f has these 2 parameters a and b, okay, delta depends on a and b. Okay. Now, the prescription, choose a and b so that delta is minimized. Okay. So, that is dou delta by dou a at fixed b is equal to dou delta by dou b at fixed a equal to 0. Okay, so that is the prescription for the choice. Okay, and this is basically, this method is, so when you set dou delta by dou A equal to 0, okay, you will get so this will give you two equations from which A and B can be determined. Okay, because there are two equations, two unknowns, A and B can be determined from this. Okay. So, for example, if f of x equal to A x plus b, then what you have is delta is equal to sum over I y I minus A x I minus b whole square. So, now what you can do is you can expand this sum over I y I square plus A square x I square. Well, okay, you don't actually need to expand it. We'll just leave it like this. Okay. Now, now let us calculate dou delta by dou A equal to 0 equal to, now if I want to take the derivative with respect to A, so the derivative will go inside this sum. So, I have sum over I, okay, and now I take the derivative with respect to A of this. So, I will get twice y I minus A x I minus b into, now derivative of this with respect to A is minus x I. Okay. So, what this gives you is the following. Now if I multiply it out and I cancel the factor of 2. So, I get sum over I x I y I, I am taking the minus 2 factor, I am cancelling the minus 2 factor. Okay. So, sum over x I y I, and then I will write this explicitly. So, minus A sum over x I square minus b sum over x I equal to 0. So, I just wrote it in this way. In other words, you will get A times sum over I x I square plus b times sum over I x I is equal to sum over I x I y I. Now, if I do dou delta by dou b equal to 0, okay, then what I will get is something very similar. Okay. So, so I will get sum over I twice y I minus A x I minus b, okay, and now I will just get a 1. Okay. So, derivative with respect to b is just 1. Okay. So, this equal to 0. So, in other words, I can write this as so if I try to write it in the same way, I will get A times sum over, so let me call this equation 1. So, what I will get is A times sum over I x I plus b. Now, you have sum over I of just b, okay, that is just n, okay, and this is equal to sum over I y I. Okay. So, these are the two equations that we got, and we can solve for A and B. Okay. You can solve for A and B. This is a simple, this is just so you know the x i's and the y i's. So, you know all these quantities, you know this, you know this, you know all these quantities, and so you can solve for A and B. So, this is the least square fit procedure that can be used to fit any arbitrary function, okay, in terms of choosing the right parameters for the fit. Okay. And this is something that is used regularly, okay, and in fact it is so common that most of the plotting programs, okay, like Excel, Mathematica, MATLAB, etc., they have inbuilt fitting functions which are based on least square. Okay. So, you can fit to a linear, quadratic, any polynomial, or you can fit to any exponential, you can fit to trigonometric functions, you can fit to many different functions. But what should be kept in mind is that you are trying to minimize the square error. Okay. So, the assumption is that your data is distributed like a Gaussian random variable. Okay. So, that is an underlying assumption in this also. So, the last topic that I want to do as part of this module is that of correlation functions. Okay. This is a little different from the error estimate, but I just wanted to mention this because it is something that is used very widely in statistical mechanics. So, here what we said is that suppose you have so go back to your distribution functions. So, you might have something like a variable x, and it might be having a distribution function f of x. Okay. And what you say is that integral f of x over whatever the range of a is, let us say a to b dx equal to 1, and average value of x is integral a to b x times f of x dx, and this is normalized, this is average, and you can take any arbitrary moment. So, I can take average of x raised to n as or average of any function of x g of x as integral a to b g of x f of x dx. So, this is average of g of x. Okay. Now, suppose you had two variables x and y, and let us say they had a joint distribution function f of x y. Okay. So, this is a joint distribution function. Okay. Then what you would expect is that integral let us say I will say a to b f of x y dx dy, and then we will have another integral c to d dx dy equal to 1. This is normalized, and you can ask average value of x is equal to integral c to d integral a to b x f of x y dx dy. Similarly, I can write average value of y as integral c to d integral a to b y f of x y dx dy, and I can ask I can also write average value of any function. So, g of x is equal to integral c to d integral a to b g of x f of x y dx dy. Similarly, I can write any function h of y, I can write its average as integral c to d integral a to b h of y f of x y dx dy. Now often you are interested in looking at the independence or relative effect of x on y and vice versa. Okay. So, you want to know whether x and y are two independent variables or they are dependent variables. So, if x and y are independent, that implies f of x y, okay, this can be factored, and if it is factored, I will call it as f x of x f y of y. So, it factors into these two terms. Okay. If x and y are not independent, okay, then you can't have this. Okay, but the question is, can we measure how dependent they are. Okay, so, can you get a measure of how dependent these two variables are? Okay, and this is where this is called the correlation function. So, the correlation function is actually closely related to this, but let's motivate that. So, if x and y are independent, then average value of x y can be written as average value of x times average value of y. Okay. So, this is fairly straightforward to show, because average value of x y will be equal to, so the proof here, integral c to d y f y of y dy and integral a to b x f x of x dx. So, if they are independent, and so this is average value of y times average value of x. Okay. So, if they are independent, it is this. So, we defined we can define a correlation as average value of x y minus average value of x times average value of y. Okay. So, this measures how independent, how dependent x and y are. Okay. So, if they are completely independent, okay, so if independent, then correlation, I will just call it C of x y, then C of x y equal to 0, otherwise C of x y is not equal to 0. And this is one way to call to estimate the correlation. Sometimes other definitions are used, other definitions of correlation functions. So, sometimes just this is called the correlation function. Sometimes you take this and subtract the average, that is called the correlation function. Sometimes what is done is you define it as x times y minus x y divided by, what is done is square root of x square y square. Okay. So, sometimes it is defined this way, okay, and so on. So, this ensures that correlation function. So, this ensures C x y between 0 and 1, okay, 0 or rather minus 1 and 1 and 1. Okay. So, there are several other definitions, okay, but essentially this quantity in all these, okay, it is this average of x y, how different it is from average of x times average of y is a measure of this, of the relation between two variables. Okay. So, this is very widely used in so one example is time correlation functions. For example, you might ask, suppose you have a collection of several particles in a box. Okay, suppose you have a box with lot of particles and many particles, and they are like in a typical liquid, okay, and all these particles are moving with some velocity. Then you can ask, so velocity autocorrelation function. So, this is you take the velocity at time t of any particle, and you take the velocity at time 0 and you take their product and you average this. Okay. So, this is velocity of any particle. So, I can put an I if I want. Okay. So, this is the velocity of any particle, and if it is a vector you can dot the vectors. So, this is called a velocity autocorrelation function, and this is widely, this is a very well known quantity. Okay. Now, now time correlation functions are really important, okay, for various reasons. Okay. One is that the time correlation functions, okay, I will write them as TCF. Okay. These are related to transport coefficients. This is what is called Green-Kubo relations. Okay. And also time correlation functions are related to spectral densities. This is what is called a Wiener-Khinchin theorem. Okay. So, actually there are several time correlation functions, not just velocity. You can look at time correlation functions of position, of density, and so on. And these time correlation functions are something that you will see very often when you are doing when you are actually doing research in statistical mechanics. Okay. So, they are in fact one of the foundations of non-equilibrium statistical mechanics. Okay. In any case, the point is, correlation functions are ways to estimate the relation between variables. So, they are generally useful, okay, and in particular time correlation functions can give lot of interesting information. Okay. So, I will conclude the lecture part of module 11 here. So, in the next lecture we will recap all the things that we have learnt, and then we will do a few practice problems. Thank you.